Hello, my name is Henson. I am a graduate student from the University of Southern Mississippi. My co-authors are Dr. Amer Dawoud and Dr. Ahmed Sherif, professors at the University of Southern Mississippi. We present a privacy-aware and hardware acceleration-based authentication scheme for Internet of Drones for the IEEE Metacom conference. Through our table of contents, we will go through an introduction, our purpose, system model, proposed scheme, software and FPGA devices, results, comparison of other works, conclusion, and finally, references. For our introduction, drones are increasing presence in today's world. They're becoming more affordable and efficient to the average user. They're also becoming more interconnected through internet and cellular networks. And also, large companies are implementing them in their workforce. Then we have the idea of Internet of Drones. A drone infrastructure over an area or several areas. This provides control and access over the internet or cellular networks. A few problems that this imposes is unauthorized use on this network or unauthorized data collection of the different drones and privacy issues. For our purpose, we create a privacy-aware and hardware-based authentication scheme using the k-nearest neighbor algorithm, KNN for short, for Internet of Drones, or IOD for short. We apply a hardware acceleration techniques to the algorithm using a Field Programmable Gate Array, FPGA for short. We start with our system model composed of three parts: our network model, our threat model, and our design goals. In the network model, we have three entities. The remote drone. Its purpose can be many things, such as delivery, reconnaissance, and etc. However, before the drone can be used in our system, it has to be registered with the registration authority, as shown in step 1. After registration, it will be able to send the authentication request to the authentication server over the network, as shown in step 4. The network tower is used for communication purposes between the remote drone and the authentication server. The remote drone then uses the KNN algorithm during the authentication request to encrypt its identification information before sending it to the authentication server during a request. Our next entity, which is the registration authority, its purpose is to create and distribute secret keys to the remote drones, as shown in step 2. The registered drones encrypt each drone's IDs using its secret key, and then pass the encrypted data to the authentication server, as shown in step 3. Next, we have our authentication server. The authentication server is used to store the encrypted IDs for all drones received from the RA. When a remote drone sends an authentication request, the server will take the drone's authentication request and perform a dot product operations between the authentication request and all other drones' encrypted IDs stored within the server, as shown in step 5. And lastly, the authentication server will reject or accept the request after finding the results of the dot product search, as shown in step 6. If the authentication server finds that the drone is not registered or authenticated, the network tower will not accept any information from the drone. The next part of our system model is our threat model. Our attackers are internal, and such as the authentication server or other drones, and they're considered honest but curious. This means that they will carry out our scheme honestly without interfering with the system and causing disruptions to the scheme. Although they may be honest, they are also curious and attempt to deduce encrypted information within our scheme to know sensitive information, such as the remote drone's ID and secret keys used for encryption in the KNN algorithm. The last part of our system model is our design goals. Our proposed scheme should achieve the following: scalability and efficiency, index confidentiality, and authentication request unlinkability. Starting with number 1, scalability and efficiency. The scheme should be able to search through a large number of encrypted drones' IDs in a short amount of time, and the size of the authentication request should be small to reduce the communication overhead of the scheme. Next, we have index confidentiality. The authentication request information of the drone's IDs should be indecipherable for the attackers, who should not learn any information about the drones. And lastly, number 3, authentication request unlinkability. Even if a drone sends 2 or more authentication requests to the authentication server, an adversary should not correlate these requests to the same drone. Next, we have our proposed scheme, which is composed of several parts. are registration and key distribution, the registration authority identification, encryption, process and upload, the authentication request, and the authentication process and results. Starting off, we have the registration and key distribution. This is where the drone will take its identification information to the registration authority to be registered. It uses its unique binary vector ID of 128 elements, and this size can be changed later on to meet different levels of security. The ID is converted into a unit vector by dividing each element by its Euclidean norm. Then the RA, registration authority, will create the key, and the size is determined by the drone's ID size. The first part is a binary vector S of 128 elements. This is used later on to split the identification information in both the RA and drone encryption processes. The next part, 6 matrices are created of 128 by 128 size, and their inverses. They are type double, and the values of each element are between 0.01 and 1. Then, to continue on, 4 additional matrices of 128 by 128 size are created. The first 2 are type double and filled with elements between 0.01 and 1, and they're m-I and m''I. Then the following 2 are created by subtracting the inverses of m1 and m2 from m''I and m''I. This creates m''I and m''I. Then finally, the registration authority has its key, and then the drone key from the RA is distributed to each drone. Please note that the drones receive the S binary vector and the product of parts from the RA key, as shown above. Next, the registration authority takes the drone's identification information, encrypts it using K-NAND algorithm, and then finally uploads it to the server. So first, the drone's unit vector ID is split into 2 vectors. Using the binary vector S, if the element is 1, it sets the 2 vectors equal to the elements of the unit vector ID. Else, if the vector inside of S is 0, then in that position, the first vector is a random number between 0, 0, 0, 1 and 1, and the second vector is equal to the element inside the unit vector at that position minus the element at the same position for the first vector. After it is split, second is we create the indices. There's 4 indices that are created using the following formulas below. And then third, those 4 indices are combined into 1 index. And lastly, the RA will upload the encrypted identification information to the authentication server. Next, we have the authentication request done by the drone. This is similar to the previous slide. First, the unit vector ID is split into 2 vectors. If the element of the binary vector S, K, is equal to 0, then the first 2 vectors are equal to the elements inside the unit vector ID at position K. Else, if the binary vector SK element is equal to 1, then the first vector, a random number, is created to 0.01 to 1, and the second vector is taking the element of the unit vector ID subtracted from the random number created in the first vector. Second, we transpose the 2 new split vectors, Q-U and Q'-U, into Q-U"-T and Q-U-T. Third, we encrypt the ID using the following formulas below, creating 4 indices, T1, T2, T3, T4. Fourth, all 4 of those indices are combined into 1. And lastly, a request to the authentication server is made. Note that the indices created here are all column indices. The last part of our authentication process and results. So the drone makes an authentication request and sends its encrypted identification information to the server. Then the authentication server uses the dot product using the drone's encrypted identification information and all stored encrypted information from the registration authority. Then if a match is found, the server will accept the drone's request, and if no match is acquired, then the server will notify the network tower and not allow any further communication. Now, a match is only found when the dot product of the two encrypted IDs are equal to 1. The next part of our presentation is software and devices. So we started with MATLAB, and we took the Kenyon algorithm, and then we used this to compare our results during experimentation and testing for other IDEs and software. Next, I took the MATLAB code and converted it to C for Visual Studios, and this is where other testing was done, and these results were also compared with our final results. Then we used Vivado HLS. This is used to convert the C functions to hardware circuits onto FPGA, and is used to develop the RTL and IP files. It also accelerates the code to achieve lower latency and higher throughput, and generates reports for latency, cycles, utilization, and power. We also use Vivado Design Suite to synthesize and implement and to get power consumption for each device. The system that we did most of our testing on had a processor i9-990K CPU at 3.6 GHz, 8 cores, 16 logical processors. GPU, a GA GTX 1080, 1721 MHz, 2560 CUDA cores. Our RAM, G-Scale 4 series, 32 GB, DDR4 3000. A Samsung M.2 970 Pro, 1 TB, was used for storage. Motherboard, Gigabyte Dexinaire Z390, and OS was Windows 10 Pro. Next, we have the FPGA devices and resources of each device. We used a high-end Kintex UltraScale Plus KCU116 at $2,995, a Xinx UltraScale Plus ZCU104 at $1,554, and a Nexus AC100T at the low end at $229. And this is the different resources that they use for our processes. Finally, moving on to the results. We have our differing software results. This table represents the results of the dot product search that the authentication server does for the authentication request. This is done through 200 encrypted identification information to matches found. In this result, you see the Kintex and the Nexus perform a lot better than MATLAB and Visual Studios. Next, we start on the utilization of each device. The Kintex 116, as you can see, we barely use the resources on this device. It is the higher end and has a lot more resources than the other devices. Our mid-tier device is our Xinx 104 and its utilization, both for the encrypted index and the index search. It uses a little bit more of its resources because it has less than the Kintex. And finally, we move on to our Nexus A7, which is our low-end FPGA that costs a lot less, and it has a lot less resources. As you can see, the utilization is apparently higher than the other two boards. Then, moving on to latency, we have the latency of the index encryption. This is for the registration authority and the authentication request because they're similar techniques. Then the latency for the index search, which is done on the authentication server for when the drones make an authentication request. As you can see that the server-side latency is very, very small in microseconds. Then moving on to power consumption for the encryption of the index as well as the index search. Since the index search uses a lot less resources and takes a lot less time, it uses a lot less power. Our next slide is a comparison of other authentication schemes to our own. This graph is latency compared to computational cost. As you can see, our high-end to low-end devices outperform other authentication schemes on the server side. In conclusion, we were able to synthesize and implement all parts of our scheme within Vivado HLS and Vivado Design Suite. We could create a privacy-aware and hardware-based scheme that can meet different consumer needs, such as affordability from having high-end to low-end devices. That can also have different levels of encryption by increasing the index size. We also outperformed other related works. And finally, our references slides to other works that we compared our work to. Thank you for your time and allowing us to participate in this IEEE Metacom conference.